one biophysicist. So this year I am trying to do it by myself, this lipid part, which is quite cumbersome, but people are doing it, and as you will find that it is quite beneficial also, because it can give ready information about the state of the lipid. You don't have to take it to isothermal titration calorimetry. How, in which state the lipid is there, you can readily get an approximation by doing X-ray crystallography of the lipid bilayer. Again, the process is complex. Okay, so let's start with crystallography proper, and then we'll take up that one. And if you can remember, we have done crystallography last in the basic biophysics, correct? So those slides will be reused, and in between I will add few more informations. Remember the biophysics crystallography class? Forgot? Anjana?
Yes, sir.
Okay, so we are going to take that from that itself, and then we are going to add a few things. So first of all, for X-ray crystallography, you need X-ray, and I don't want this stupid bar to come at the bottom. How to get rid of it? I think we can't get rid of it. Only thing, we have to just make the slide visible in such a way that escape. If I go to slideshow mode here,
Sir, you can double click on the slide.
no, no, the thing is that I don't want this bar because it's getting cut on the bottom. No problem, as it is. Let it be like this. So to get the X-ray, what generally we do, we take a vacuum tube, as we see over here, and in the vacuum tube there is a cathode. I remember cathode as the place where cation goes, which is highly negatively charged, and one anode. I remember anode as a place where anion goes, or negatively charged ion goes, which is highly positively charged. Inside there is vacuum, and what you do, you heat up this cathode like anything. So when you heat it up, what happens that electrons get dislodged from this cathode, and it start running towards the anode. Why it runs? Because anode is highly positively charged. So as it is running, what you are doing, you have just let me draw it. You just kept a heavy metal like copper, chromium, etc. in their path, which is neutral. This is the copper nucleus, and there are a lot of orbits on which electrons are moving, and these are the electrons. There are many orbits are there. How many orbits copper have? I forgot. Many actually. So what will be happening that as these electrons are going from this side to that side at a very high speed and very high energy, it can dislodge any one of these electrons. Nonsense. What is this? Just a second. এই অফিসে মিটিং আছে আধ ঘন্টা, এই 2 ঘন্টা বাদে করছি। এই মিটিং এ আছি, পরে কথা বলছি। Okay, so what is going to be happening that as these electrons are moving, it can dislodge, it is so powerful, even it can dislodge electron from this s orbital. This electron will come and it may take out or hit an electron and let it go out from this s orbital. So what is going to happen then? there will be a energy gap will be created, but this phenomena is not very common actually. Most of the cases electron will be taken out from the outer orbitals and they will be put back. So most of the energy will be wasted, but in some cases what is going to happen, an electron of a very stable orbit will get kicked out. So if you plot an energy value, so an electron which has very low energy will be put to a very high energy by hitting with an electron that was flowing from this cathode towards the anode at a very high speed and very high energy. It is so high that the energy will it can kick out even the s orbital electrons. So, the electron from a very stable state will be put into very excited state. So when it will fall, what is going to happen? It will create and it will release an energy which is extremely high energy. So extremely high energy means extremely low. So energy is equal to h nu by law of physics. Nu is the frequency or h light speed of the light by wavelength. Extremely low wavelength. One light will be created, and this light is X-ray. So the X-ray will start emitting from this copper or chromium or any heavy metal that you have kept inside this path of this extremely fast moving electron that was dislodged in this vacuum tube. Okay, got my point? And this is the intensity profile. Suddenly you see these are the profile of this electron. They are this phenomena is not very common. You see, it does not fall in the general pattern of the energetics of this system. It comes like a sharp peaks like this k alpha, k beta, these peaks you are seeing. This denotes from which orbit the electron has been dislodged. So most of the energy in this process will be lost, but 99%, but 1% of the energy will be very useful when it comes and dislodges electron from a very stable orbit. And when that electron comes back, it releases a light which has extremely high frequency or extremely low wavelength, and that light is X-ray. Got my point? Srihanjana? Srishti?
Sir, got it.
Okay, fine. So this light is very important. Why? Because here the wavelength is too small. Remember the wavelength of regular light? Regular light, it is around visible light 400 to 700 angstrom. Angstrom or nanometer, I forgot. 400 to 700 nanometer. So here you will get around 2 to 4 nanometer in case of X-ray. So the wavelength is so small that it comes in the range of the length of those chemical bonds. And when you studied about light microscopy, I think whosoever taught you told you that the resolution of the object you are going to see or visualize depends on the wavelength of the light you are using. So that is why in visible light it is very difficult to differentiate between objects which are more than 200 nanometer apart from each other. But in X-ray you see it is very tiny. So you can study in length which are 1 to 10 nanometer. apart. That is various atoms and molecules inside uh, inside a organic or inorganic compound. But the trouble is that there is no X-ray lens available. So this cannot be used as a microscope, and we have to use this technique in some other way that can be useful for us to visualize these electronic arrangements. And there comes X-ray crystallography. So here we are going to use the diffraction property of this light to study, to visualize how the atoms are arranged in a particular type of molecule. Okay, next. So crystalline and amorphous solid. So solid can be of two types. One of them is crystalline, in which the unit of that solid, I am coming what I mean by unit of the solid, is arranged in regular and repetitive arrangements, and it has a long range of atomic order. Long range means how long range? So I was discussing about graphite in the other class. So in graphite you have one layer, after that one layer, after that one layer, like that millions and millions of layers will be there. So these are crystalline solid, and there are some solid where it will be not that millions of layers, few hundred of layers, and in some cases it will be the the units of the solid will be totally arranged in an irregular manner. So one common example is glass. Glass is solid, but in glass all the, it's made up of silicon, I think oxide, something like that. So all the silicon oxide units will be arranged like this. So this is the silicon interface. You see that this is amorphous interface of the silicon. So both sides it is crystalline. In between you see the arrangement of the units are not in order. They are disordered. Again, this was taken by high resolution transmission electron microscope. Uh, but crystallography is even better in some cases, because in transmission electron microscope you have to give a very thin layer of this arrangement to see the relative orientation of these atoms. But in crystal it can be of any shape, provided the X-ray beam can penetrate that. Whereas on the left you see it is a crystalline solid. So it is a mixture of strontium and titanium. So brighter atoms are strontium and darker ones are titanium. You see that they are arranged in a very regular manner, and this regularity will not be limited to just one plane, but in millions of plane up and down of uh, uh, so up and down of this layer, you are going to get the similar arrangement, and that is how crystalline object differs from amorphous object. And one very good thing about the crystalline object is uh, that in the just let me turn on the video. So along the plane where these molecules are arranged, layer after layer after layer after layer, like billions of layers, it will be very hard in those regions. So and but amorphous liquid will not be that hard. So if you take glass, plain glass, uh, just buy it from paying few rupees from any grocery shop, and if you hold the glass like in your hand and you just tap it, it will be getting broken very easily, correct? But if you the same thing you do for your mobile phone, the same glass, it is crystalline, it is quartz glass. So in that case, what the manufacturer is doing, So they are arranging the silicon dioxide in such a way they get this kind of a layering arrangement, this kind of arrangement. So by tapping the mobile phone, it is very difficult to break it. So how mobile phone glass breaks? So this is a mobile phone glass. Everybody can see it.
Yes, sir.
So can you notice where the cracks are getting generated more?
In the corner.
Yes, on the corner. So if you target from this side, so there are less number of layers. So all the time crystalline objects are very tough along the thickness of the layers, but it can be easily broken from the side. So that is why when mobile phone glass cracks, it only cracks from the side, not from the center. Never, unless and until if you do some sledgehammer and try to poke it. But had it been a regular glass, if it can break from anywhere. So that is the difference between a crystalline solid and an amorphous solid. Okay, next. Everything has come. Stupid. Just a second. Okay. So as I was telling, there are amorphous solid and single crystal solid. In the single crystal solid, the periodic it is periodic across the whole volume, and something are there which is called polycrystal, which is regular, but it is not repeated along through and through the length and breadth of the solid. It is periodic in one range, again the periodicity is lost, again periodic, and amorphous solid it is not there will be no arrangement found in any place. The common example is glass. So the crystal lattice of the entire solid is continuous and unbroken to the edge of the sample with no grain boundaries. And in case of amorphous solid, polycrystal, there are many small crystal or grains. Each grain has different crystallographic orientations. There exists atomic mismatch within the region where the grains meet, and these are called the boundaries. You are going to get this kind of arrangement in the membrane. So membrane is polycrystalline. In one of the states. Membrane can have various states. Again, I'm going to take that at the last, but just I'm telling membrane also can be analyzed by X-ray crystallography, and in that case we will be encountering a situation which is not a pure crystal but a polycrystal, and there exists atomic mismatch within the region where the grains meet. It is called the boundary, and across grain boundary orientation of the crystal will change. Now, when this X-ray, what we just generated, hits this crystal, it gets diffracted. Why it gets diffracted? I am coming to that. But diffraction occurs when light is scattered by a periodic array with long range order, like this single crystal type of variants, producing constructive interference at specific angle. And we, by measuring those constructive interference, we can conclude by doing some mathematics how the atoms are analyzed inside each of these single crystals. For polycrystal you can do it, but it will be much more difficult than if the arrangement is like single crystal. So in case of protein crystallography or crystallography of salts, we will be encountering this single crystal, but when we go to crystallography of liquid, we are going to encountering this type of nonsense. So the situation will be much more difficult, but there are some other very what is called very thoughtful hypothesis people have proposed, and it was applied, and by our luck we can tell, we found that those actually worked for lipid crystallography, and that helped us helped us in solving which could have been unsolvable. Anyway, we are coming to that later. So, crystal is any solid material in which the component atoms are arranged in a definite pattern and whose surface regularly reflect an internal symmetry. This is the definition of a crystal. Now, take any crystal, sodium chloride you take, diamond you take, graphite you uh, take the crystal of a protein. In all the cases, a crystal can be thought of made by something called an unit cell. The unit cell may or may not be existing on its own. It can be a totally hypothetical object. But the good thing about this unit cell is that if you can locate the unit cell, like the unit cell you see over here, by translating along the x, y and z axis. So, you take the unit cell, you remove it on the x axis through and through, then shift it around y axis, again put one next to each other. Just by moving this unit cell and stamping that in 3 dimension, you can construct the entire crystal. Get my point? So, this is just like a stamp. You know a stamp? So, it is a 3 dimensional stamp for the crystal. Suppose the crystal is like very big, anything. Uh, Suppose this is the crystal. This is a crystal. So, what can and if suppose this is the unit cell of this crystal, suppose this is the unit cell of this crystal. So, now what is the good thing about this unit cell concept is this object, just you take it and stamp it on 3 dimension, little bit move it, again stamp it, again move it, again stamp it, like that, by going by x, y and z, and each time you move little bit, you stamp in 3 dimension and then move again you make a stamp of this and move little bit. So, like that, by stamping this unit cell along the length and breadth, that is by x, y and z axis, you can reconstruct this crystal. But you see here, the unit cell per se by itself, it does not exist. It's not like a protein domain. It does not exist physically. You cannot break and get this unit cell, because you see here in this unit cell, what we have done, we have got 1/8 of each of the atoms that is making the crystal, which is logically impossible. But if you take an arrangement like this and just move across x, y and z direction, you are going to reconstruct this crystal, and this is the concept of unit cell. Did you get my point?
Yes, sir.
Okay. So, unit cell, I don't like this nonsense. It will go. So, unit cell is this basic repeating unit of a crystalline solid is called the unit cell. A unit cell consists of a solid consists of large number of unit cells arranged in 3 dimension. So, this is the unit cell, and you see that if you go x, y and z, you can reconstruct. So, this solid is actually a repetition of this unit cell. The atoms in a crystal are arranged in a periodic array with long range order and can perform diffraction. So, this atomic arrangement in a crystal is actually a repetition of this unit cell in along x, y and z direction, and as it gets arranged, it gets arranged into a very long range regular repeating pattern, and due to this regular repeating pattern, whenever X-ray falls on it and gets diffracted, that diffraction also comes with a regular repeating pattern. So by if we can catch that diffraction, you can easily come back to the crystal and find out the location of each of these unit the where the atoms are located. So in case of crystal, these points are called lattice point. So in this lattice point, the atoms which makes the crystals gets located. So and they diffract the X-ray. So as they diffract the X-ray, they diffracts obeying the regular arrangement of atoms in these crystals. They are arranged in a you see that they are all arranged in a particular plane. This is one plane, this is one plane, this is one plane. So one plane after the other, like this in z direction. If you take x direction, it will be on the x direction. For y direction, they have arranged in a particular order, and due to this particular order, whatever light falls on it gets diffracted following a particular order. So if we can catch the light which is diffracted, we can easily come back and solve the three-dimensional structure of this crystal. Correct? Correct or not?
Yes, sir.
Fine. So unit cell is the smallest unit of a volume that permits identical cells to be stacked together to fill the space of the crystal. By repeating the pattern of the unit cell over and over in all direction, the entire crystal lattice can be reconstructed. So now my question is, how many types of unit cell can be there? Any guess for a crystalline object? You will be surprised to know, like we have some how many type of atoms we have in periodic table. 100 and I think 11 till now purified, correct, or more. So like that, the number of unit cells also are very limited. Why? Because in unit cell we have to pack the atoms, and there is no way we can waste space during while packing the atom. So there are definite rules by which these atoms can be packed, and due to these rules, there are only 7 basic type of unit cells are possible: simple, cubic, tetragonal, orthorhombic, like that. There are 7 types as you see over here, and wavelength of X-rays are similar to the distance between atoms in these unit cells of this crystal. Therefore, we use X-ray scattering to study the atomic structures. So, these are the basic shapes, these 7 types in all the crystalline objects that we get in universe. In universe, why they are this small in number? Because these are the only shapes that can be stacked one against each other without wasting any space between them. Correct? So that is why this is only 7 types. And now I am taking the first one, the simple cubic one. In the simple cubic, there are 3 types of arrangement possible. One is a simple cubic, one is the body centered cubic BCC, and one is the face centered cubic. In the simple cubic lattice arrangement, the atoms of the crystals only occupy the 8 corners of this unit cell. But in case of body center cubic, not only they occupy all the 8 corners, but also the center part of the unit cell. And in face center, not only body, but also the, as you can see, the middle part of this, each of these surfaces, middle of the surface, there are another atom which will be located. So this face centered one is the most compact form of crystal. In most compact form of crystals, we get this kind of face-centered cubic arrangements. So the F cell is very important because it is the pattern for cubic closest packing. There is no centered cell because such a cell would not have cubic symmetry. So here there is no centered cell, but you see in all the surface there is 1 1 1 1 1 1 atom is located, correct. So this is the most compact and most simple is the simple cubic structure. It is not very much used in nature because though in simple cubic you can attach one of the lattice against the other without wasting any space, but inside this unit cell you are wasting space, and then nature doesn't want things to be get wasted. So only in case of metal polonium you get this kind of simple cubic set, and funny it is also P. But whatever else crystal we see are either body center cubic or face center cubic if the crystal has cubic interface. So this is the simplest of the all the arrangement. More complex arrangement is you can be found in other ones like sodium chloride. It is simple cubic. In urea we can get tetragonal. In case of iodoform orthorhombic, boric acid triclinic, sucrose monoclinic. So all these are arrangement which is more complex than the simple cubic arrangement that we just discussed. So now we are coming to X-ray, and this photograph I think we have shown you in your basic biophysics class that William Röntgen, he was studying X-ray, and he found that when he he was using the cathode ray tube for generating X-rays. So all his X-ray films, or all is not, I cannot tell it X-ray film. Excuse me, the photographic film getting exposed, but the source of the light he was unable to detect. So he named it X-ray, and I think we discussed this story that she took Madame Röntgen's hand and put in on the path of the light, and he found that it is an electromagnetic radiation because so wherever there it is getting encountered with atoms having higher atomic number, that is more electrons, it is getting diffracted. So in Madame Röntgen's hand you have flesh, bones and the wedding ring. So the flesh is made up of carbon, hydrogen, nitrogen, oxygen, so it hardly diffracted anything. Bone is calcium, little bit more in atomic number, so it had diffracted some of the electrons, some of the photons of the X-ray. So that is why you can get the shape, and the wedding ring is made up of gold. So it is the heaviest, lot of electrons are there, so it has scattered more, so you can get a darker patch on the hands. We discussed this. You remember Srishti or Snehanjana? This one.
Yes, sir.
Okay,
Remembered.
okay. So what is going on here? So here, this is the electron, which is this is one electron of any atom. So the electrons vibrates inside the atom. Now, if the vibration frequency matches with that of the X-ray photon frequency, what is going to happen? The X-ray photon will be scattered in various direction by this oscillating electron. So the incident beam of X-ray will be scattered in all 360-degree spherical location, and a tiny portion will be transmitted, and that is why we get a image like that. So this is the old image. In modern day, what we do, we when we take X-ray, we take this transmitted beam, the reduction of the frequency, and then we invert the image, and this is the modern X-ray image of the hand. So this is for imaging applications of the X-ray, but in our case, in biophysics, we are not only interested in this transmitted ray, but all the diffracted rays also. Why they are diffracting? Because they are diffracting, interacting with the electrons present on these atoms. And as in the crystalline objects, these what is called lattice positions are occupied by those atoms following a definite rules. Then it was thought that by measuring these diffracted beams of X-ray, we could get positional informations of the centers where from where the X-ray beam is being scattered. So that gave rise to the X-ray crystallography. In X-ray crystallography, what we do, we take the crystal on a mount and we put a X-ray beam, and as we put the X-ray beam, depending on the lattice position of the atoms present in the crystal, it will start diffracting. That is throwing away the linear beam of X-ray, throwing away linear beam of X-ray in all directions. So that depends on the arrangement of the planes. So now what we do, after we get this arrangement, we slowly rotate this crystal. So suppose in one condition the planes are 90 degree at 90-degree angle to the X-ray beam. So when we are rotating, suppose this is the object again, and the lattice planes are all at perpendicular to the X-ray beam, and then we slowly rotate it. So as we rotate it, the lattice planes will starts coming at various angles, and since it is coming various angle, the nature of this diffracted lights also changes. So and we then measure all these diffracted light positions, their intensity, and comes back calculate back the arrangement of the atoms in various planes in the crystalline object. So by solving that structure, we can get the three-dimensional arrangement of those atoms inside that three-dimensional crystal. So this is the nutshell of the process. So X-ray crystallography is a method of determining the arrangement of atoms within a crystal, in which a beam of X-ray strikes a crystal and causes the beam of light to spread into many specific directions. From the angles and the intensities of these diffracted beams, a crystallographer can produce a three-dimensional picture of the density of the electrons within the crystal, and from the density of the electron, he can always calculate back where are the atoms are located, because atoms are located in those places where there is most density of the electron, correct? So if it is if a calcium atom is located here, this region will be more electron dense than a hydrogen, correct? Because in calcium we have how many electrons surrounding it? What is the atomic number of calcium? 40, I guess, na?
Sir, 20.
20. Oh, mass is 40, correct. Sorry. 20. So 20 electron will scatter more than 1 electron. So you can easily determine that if it is calcium or a hydrogen. Because X-ray have wavelengths similar to the size of the atoms, they are useful in exploring within the crystal. Again, it is from the previous years. So for X-ray crystallization, we have to make crystals of the object. So there are various techniques available. So one technique is hanging drop method, one is sitting drop method. This is sitting drop method. So what is done over here, there is a well, and this well is sealed off airtight and filled it with very high concentration of sodium chloride, and polyethylene glycol, and here the compound was put at a lower concentration. So protein plus lower concentration of sodium chloride and PEG. So if you keep like that, what is going to happen? This portion will vaporize more and this portion will vaporize less. So slowly and slowly the concentration of, if you are doing for a salt crystallization, you can put a salt over here. For a protein, you can put protein over here. Slowly the concentration of the protein will increase, and at a given point of time, what is going to happen? The protein will start precipitating out because it will reach the solubility, maximum solubility limit of proteins, and as it is precipitating out, it can precipitate out as amorphous compound, or it can arrange itself depending solely by chance or luck and form protein crystals, and using that crystal you can solve the structure of the protein. So this is how we set up crystals, but this process started long back when people started using this technique for X-ray diffraction. They thought they can solve structures, and the first experiment was done by Max von Lohe and Walter Friedrich. What they have done, they have taken copper sulfate. Copper sulfate crystal, there is no need to make it, it is available in plenty, and they shoot X-ray on it, and they found the diffraction pattern. And this is the diffraction pattern what they found. I think we discussed in the last class also. It looks nothing actually, but you can see there are regular repeating intervals on which the X-ray beam has been scattered. In at the center you have the transmitted beam, so it is becoming too bright, and so as it is too bright, when it fall on the X-ray plate over here, so it has become a dark spot like this. Light has fallen to other location also, and but it has fallen by a definitive pattern, correct? So the process was found to be working. But the trouble with this copper sulfate was, with the bad luck of those scientists, that the arrangement of atoms in copper sulfate unit cells, and how those unit cells get translated into the structure is very complex. And that time the X-ray beam that was X-ray was used on those primitive time. It is, I am telling about 1930s. They were of low power. So that is why they failed to resolve any one of those spots. So after that, scientists have tried doing the same experiment with zinc blende, and you can see that there is excellent regular repeating pattern. We can get it by shooting X-ray on a zinc blende crystal. And can anybody tell me why there is a very solid black spot right at the center of this scattering pattern?
Nucleus.
Uh-huh.
So the neutron and the nucleus of the atom.
No. Let me tell you, draw it again. So you are shooting the X-ray. Here is your crystal. So, and there is an atom which has electron. The electron is diffracting the X-ray all the sides, but some of the rays are getting transmitted, correct? Not all rays diffracted. These are the diffracted spots for the diffracted rays. So this is the transmitted ray, correct? One person, a portion of the ray will always get transmitted. If it is 100, say 10% is transmitted and rest is diffracted. So these are the diffracted rays where they have fallen, and this is the spot for the transmitted ray. Got my point?
Okay.
Okay, so we are going back. We are going to take a very short break right now. We are going to come back around 10:55. So 11:55. Okay, so don't go away. We will join in the same meeting at 11:56. Okay, so let's start again. Everybody back?
Yes, sir.
Okay. Okay. So we are there. We told about the zinc blend, which gave better diffraction pattern, and from this diffraction pattern, uh, the structure of arrangement of zinc and sulfur in this crystal was solved. How it was solved? So it was solved by Bragg's law, and to get that law into context, we just have to take help of a simple reflection analogy. So every one of us know about reflection, that uh, light falls and the incidence angle and the angle of reflection is equal. So same thing we will be now discussing about, taking into account not the mirror but a layer of molecule in a crystals. How many layers? Millions of layers. And we are putting an X-ray beam on it, and as the X-ray beam is passing through the crystal, in each layer it is encountering, they will be encountering a set of atoms, and in those atoms there will be electrons. So either that electron will diffract some of the X-rays and allow the rest to pass, or it may not diffract also. So from each layer, therefore, diffracted X-ray beams will emerge. One portion diffracted, rest portion transmitted. Again from the next layer, one portion diffracted, next portion transmitted. Like that, it will keep on going from one end of the crystal to the other end. Okay. So for the simplicity, what we are now taking, we are just taking two rays instead of this many, and suppose the ray number 1, it is getting diffracted from the top layer of this crystal arrangement, which is also called the crystal lattice, and this two layers is separated by a distance d. And remember, this is not a single linear layer of molecule, it is actually a plane, and the it's just a section of a very big three-dimensional arrangement. Just a plane has been shown for simplification. Okay, so the two rays that got diffracted from the layer 1 and layer 2, and remember, this is not a full 100% diffraction. The rays will also travel to subsequent layers, as it has been shown over here. We are just taking the first encounter of these two rays with the crystal lattice. So we we can invoke the wave motion of the rays here, and waves we know that can interfere both constructively and destructively. If the peak and trough of the both the rays are at the same location, there will be a constructive interference. But if the peak of one ray and the trough of one ray matches against each other, then these two rays will cancel over each other. So for the constructive interference, what is required? For the constructive interference, it is required that the path traveled by these two rays. So see here, the first ray has come over here, got diffracted here and going like this. The second ray has come like this. Up to this, the path is same, but it has to travel additional this distance. Again, additional this distance, and then the path is same for both the rays. So this path difference, this much, how we can calculate is by simple trigonometry. We told that in this layer, this in this crystal layers, these two planes, Again, these planes are called Miller planes, just a terminology, are separated by a distance d, and the ray has fallen at an angle theta. So by simple trigonometry, so this is again d and this is theta. If this is theta, then this is also theta. So this distance will be d sine theta. So when we are doing trigonometry, our teacher told that axis. So sine theta, cos theta, sine theta, cos theta. So this is the d sine theta. So the distance traveled by the second ray is 2d sine theta, and so if this 2d sine theta is equal to one wavelength or simple multiple of one wavelength like n equal to 1, 2, 3, 4 like that, these two rays will constructively interfere and we are going to get a uh, bright light spot on the X-ray film, which after you develop will develop into a dark spot. Okay. Similarly, if these the path difference is equal to not the integral multiple of the wavelength, that is 2n minus 1 lambda, that is half, 3 by 2, 5 by 2 like that, then what is going to happen? The peak of the next ray is falling on the shaft of the previous ray and they will cancel each other. So we will detect no scattering on the X-ray film. So these rays will be cancelled, no light will fall on the film and no black spot will get generated. So this is the simplest thing about this constructive and destructive interference as it goes in the layers of the crystal after we shine a light on them. But in reality we will get in these two extremes. So either it will it will be somewhere in between. So getting exact constructive and destructive interference, it is very difficult to achieve. So even if you make it constructive interference all the time, there will be slight deviation in your from your set parameter with that of the exact diffraction pattern of the light waves. Exactly that is happening over here. So here what is happening? So this is a very big layer, crystal layer, and between two layers distance is again d. And what is happening? The path difference between two adjacent rays here is coming as not full one wavelength but 1.01 wavelength. Okay, little bit more. So you have set it correctly, but it is not fallen fully one wavelength different. So but it is almost one wavelength different between the two adjacent rays. Got my point?
Yes, sir.
So from first ray to the second ray it is 1.01. So from the first ray to third ray it will be 2.02. So like that you go on in the crystal structure. So at the 51st layer the path difference is now 50.05 times the wavelength. So half wavelength. So this ray and this ray will do destructive interference. Correct? So if you measure the intensity will start here almost constructive interference, but as you go to the 50th layer you will see that the intensity of the ray is falling and you are not getting any dark spot on the X-ray film. So when intensity is high it will create a dark spot but as you go to the 50th spot you will see that there is no dark spot because there is no light, there is destructive interference. Again you will get constructive interference. So like this due to slight difference in the wavelength and the gap between these two layers, you are, even if you set it for a full wave constructive interference, you are going to, you are bound to get this kind of regularly what is called arising spots. And you may tell that, okay, I'll do better arrangement. So in my case, the path difference will be 1.0000000001 lambda, very tiny. But remember, we don't have 50 layers or 50 Miller planes in a crystal. We have billions of Miller planes. So even if a tiny 1 in 1000 or 1 in 10,000 or 100,000 difference in the wavelength also will create alternative patterns of constructive and destructive interference. Correct or not? Agreed?
Yes, sir.
Okay. So next, let me turn on the. So what we told just before concluding the previous session, that we will shine the light on the crystal, and as we are shining the light like this, so all the planes are now all are parallel, sorry, perpendicular to the X-ray beam. Then what we are going to do, we will be turning them little bit. So the arrangement of planes that the X-ray beam was encountering now will get changed. So if you turn it like this, the diffraction pattern of the X-ray also will change, because you see there is clear difference in the arrangement of these atoms. If you keep like this, and keep like that, you are getting three different types of arrangement of these atoms in the crystal lattice. Okay, so the light they will diffract will also be different, and you know in which direction you have rotated the crystal to get that diffraction pattern. So by rotating it at various angles, we are going to get various diffraction pattern, and after you get those various diffraction pattern, you can easily solve them and get back to the location of those atoms present in the crystal structure. So this is just a simple arithmetic which can be done by any crystallographer. Okay, so by doing this kind of process, the first crystal structure that was solved and which has a very big impact is that of the sodium chloride. In sodium chloride, they found that there are regular repeating arrangement of sodium and chlorine, but there is not per se any sodium chlorine bond existing, because it is an ionic compound. There are regular repeating arrangement of sodium and chlorine, no doubt, but you cannot tell there is a bond between sodium and chlorine. There is no sodium chlorine uh, like a covalent bond sitting anywhere in that. So that was itself a very big discovery in that time. So that broke the myth of an ionic bond. There is no ionic bond in per se. There are attraction between negative and positive charge, and that in a regular repeating format gives rise to sodium chloride crystals. After that, organic compounds, sorry, not organic compound, uh, compounds of carbon, I can tell, like diamonds and graphites, they also got crystallized. And in graphite you can see this kind of planar arrangement. That is why it is very useful to make pencils, etc., and for other jobs. In diamond, it's a typical three-dimensional structure. So all these structures were solved by using simple Bragg's law and arranging those planes by rotating the crystals. But problem came when the same technique was used to solve structure of bigger molecules. Bigger molecules means I am not telling about protein, like say penicillin, like vitamin D. Those are very big molecules. So they have it is not like a sodium chloride or cesium chloride, just one place, one atom sitting, and they are diffracting. So in this case, how to get this? In this case, each of these units, so if it is vitamin B12, each of this unit is occupied by a very large macromolecule, and each of the centers of those macromolecules, because the atoms that constitute the macromolecule, they themselves were scattering the X-ray in all directions. So things become very complex, and it is become even complex when we start using X-ray on protein crystals. So proteins are huge. It has thousands and millions number of atoms of various types, and each of these atoms scatter X-ray at various angles in 3 dimension. Every part of the molecule scatters in every direction. So simple Bragg law will be therefore not applicable if we want to use this technique for determination of protein structure. So what technique was thought of? So it is correct that all atoms and molecules present in the protein lattice is scattering in all direction, but we can think of summing up of all the rays that is getting scattered in a particular direction. That we can do by taking a X-ray film over there. We can easily measure what is the total flux of rays that is going over in this direction. In summary, so we are going to consider all the scattering in just one direction first. So from these points, all these points, it is getting scattered all over. So and this is the imaginary origin of this big biomolecule, and this is the length from where we are measure the which is our measurement point. So this is the location which has a particular electron density, and depending on the electron density, it is scattering the X-ray beam in all direction. That is quite obvious, and this small area has a particular volume also. So this is the electron density function, and this dx, dy, dz denotes a very tiny x, y, and z coordinate that builds up a very tiny volume in which electrons are there, and those electrons are scattering X-ray. And here it is also coming, this R is also coming, and this is an imaginary quantity I, and S depends on the orientation of these particular spots. So summing up, it has the function for orientation, functions for the location, this rho R, and a function for volume. So and this in total are the total number of light that has been scattered in a particular direction from this point. Okay. So now if we consider all the points in the particular macromolecule, then what we have to do? We have to summarize. So add up all contribution to find out the total scattering in this one direction. So we have to summarize. Summary means sum up all the points that is scattering in this direction, and this is the integration sign of for summation of scattering from all the points in the macromolecule or protein in that particular direction. It has the it has contribution for each points. So this is the electron density function for that particular point. This is the volume function, and this R denotes the angle at which we are measuring the intensity. And then we summarizing we are making a summation of all the intensities coming from all parts of this molecule, and that adds up to the total intensity that is falling in at this location. Okay. So that intensity can be measured by putting an X-ray plate. So after we get to know the intensity, then so it comes like this. This is the intensity pattern. You can see there is hardly anything meaningful what we can get over there. So this is scattered by a single molecule of a protein, but you see there is some pattern. So this pattern need to be solved to get the three-dimensional arrangement of these points, this as it is given by this rho r. So we have to solve for this rho r. Where are these points located? That has given these kind of a diffraction pattern. That we have to find out, and it was done by applying the famous Fourier transformation. So John Baptiste Fourier died long back before the X-ray got discovered, but his technique told us that okay, so this scattered light is a function of this rho, correct? The electron density of a particular point. So then, if we inverse this equation or do a reverse Fourier transformation, we can get to that point of electron density. So this is the original integration equation. What it was done? So this dx dy dz has been it is the volume function, and this is the rho r. So what they have done, they just reverse the equation or reverse transform the equation, and when you reverse transform it, what you are getting, you are getting the electron density at a particular point. That is what we want. We want the three-dimensional electron density of each and every points present in the protein. That can be easily solved by reverse Fourier transformation of this equation. So if we can get this information of electron density, suppose we get a pattern like this of electron density, comes like this only. So then what we have to do? So we know that something has gone through it. So it might be an alpha helix. So first and foremost, what we have to do from this spotty image, what we have seen over there, we have to apply the reverse Fourier transformation to get the electron density map of the big molecule. It can be a big organic molecule like vitamin B12, or it can and might be a protein also. So first thing need to be done is to get this rho r of all the points. That is the electron density at position r. So when you get that, you can draw electron density map, and after you draw the electron density map, you have to fill it up the electron density with the sequence of the particular biomolecule you are solving structure. You should know that sequence beforehand, and that is quite obvious because you only have purified the compound and gave for X-ray crystallography. So when you have purified, you know the sequence of that particular protein, correct or not?
Yes, sir.
So that has to be filled up in the 3D electron density map to get the structure of that big biomolecule or the macromolecule. So here Braggs law is still applicable. So in case of protein, so these are the Miller planes, and each of these center is diffracting, but the trouble is that there is no one atom sitting over there. There are many atoms sitting over there, and all of them are diffracting. So that is why we require Fourier transformation. So Bragg's diffraction will go on, but along with Bragg's diffraction, each and every atom present is also diffracting, and that gave rise to this kind of a clumsy pattern. And By Bragg's law and by Fourier transformation, we can easily solve and get the locations of each and every atom present in the protein, correct? And thus we can solve structures of proteins, big biomolecules like vitamin D, um, then another one penicillin. So it started all with those big biomolecules and then gradually developed in solving the protein structure, because protein structure is even more complex. So this is the first one of the first application of this Fourier transformation to solve the crystal structure of this compound diopside. Diopside is a compound calcium magnesium silicate. So the diffraction pattern was Fourier transform, and after it was Fourier transform, you see there are centers are forming like this. So these are the electron density regions. So depending on the electron density region, we can fit in appropriate cations and anions. Sorry, not cations and appropriate atoms into the center to solve the overall three-dimensional structure. So this is how it was solved. So here it is calcium, so it is very dense over there. So they marked it as calcium. Magnesium is which one? These smaller circles. Smaller circle. This is, oh, this is both calcium. There are two arrows over there, both calcium and magnesium present at this location. And then these are the silicon, oxygen. So like this, by solving the electron density map first, we can fit in the components of the crystal and get the three-dimensional structure of the crystal solved. By doing the same way, penicillin structure was solved in 1945, and extracrystalline structure solution we are not bringing over here, but that's a totally different story. But as days progressed, more and more complex structures were solved. The first protein structure to get diffracted was pepsin. So pepsin, this is the crystal structure of uh, sorry, it was not there at present, but the diffraction was done for the pepsin crystals, but the frame was lost. The first frame which of a complex protein whose diffraction pattern is known is that of hemoglobin. So in this data told us that there are regular arrangement of peptides inside hemoglobin. So before that, again it is 1938. So before that, people thought that in hemoglobin, being a component of red blood cell, it's the protein structure is, there is no protein structure present in that compound. It's a something disorderly proteins, disordered protein which no particular three-dimensional arrangement. So had it been a disorderly protein, when hemoglobin was crystal and after diffraction was done, there should not have been a regular repeating pattern, correct? But scientists did find regular repeating pattern arising in the hemoglobin structure, and that thrown away the hypothesis that the hemoglobin structure is amorphous. Okay, but the hemoglobin structure was not solved using this structure. The first protein whose crystal structure was solved was, remember, basic biophysics? Anybody remember the structure of that protein? Which one was that? It was looking like horrible. It was looking like viscera, stomach, abdomen. Yes. Who can give the answer? Srishti, remember it? Dejani, which was that? Forgot. That was myoglobin. And why it was this kind of a visceral shape? Because that time the X-ray that was shot on the crystals, you cannot get to very fine angles. So the overall resolution of the structure was very poor. They got the electron density map, but the resolution of the electron density map was very poor. So they roughly calculated at from which direction the helix is moving, but the finer details of the helix was not came into being. So that gave rise to this kind of a complex structure. But in few days from the discovery, modified structure came in which all the finer details of the three-dimensional arrangement of various atoms and molecules were found, and not surprisingly, it was found that it was following the same visceral pattern that was originally developed by originally solved in 1959 by Max Perus. So the good thing about this discovery is that when few years later, when horse hemoglobin structure was solved, it was found that the myoglobin structure is fitting very well in either of the four hemoglobin structures. So that led to the foundation of the theory that they are all actually originated from a common ancestor with a purpose for carrying oxygen. So due to evolution at later time point, the hemoglobin and myoglobin got differentiated, one become tetramer and one remained as a monomer. But this information was not possible to be acquired that time by comparing the DNA sequence of these proteins alone. Why? Because there is huge DNA sequence difference, but the fold by which this protein gets to their tertiary structure was identical between both hemoglobin and myoglobin. So for the first time, we realize that the structure function correlation that is present during evolution. So are you with me up to this? Any questions?
Sir, okay, sir.
Okay, I think we actually got it in the last class also during BSc. After that, lysozyme structure was solved, and nowadays we don't use X-ray handheld X-ray or lab-based X-rays. So we get very high power X-rays in times of synchrotrons, and there is one such cyclotrons. There is one such example is given over here. This is a diamond light source. It's a very big cyclotron. Very powerful X-rays can be emitted for very fine analysis of protein structures, and the structure of the protein that we are solving, it is also increasing day by day. So we started with sodium chloride, zinc sulfate. From there we came to pepsin, trypsin, and then came to hemoglobin, myoglobin, then bigger complex like F1, F2 ATPase, which is a mitochondrial ATP synthase. Those structures were solved, and when I was student in around 2003 onwards, ribosome structures were also getting solved. Ribosome is a very big macromolecular complex, but with the help of very high power laser as available in the cyclotrons, the three-dimensional structure of ribosomes are also solved. Now then, what is the next target? So again, if you take ribosome also plays a very tiny role in the overall proteomic arrangement of any cell. So now at present the target is to solve all these molecules in a cell in their act together. So we have to crystallize a cell and fix the locations of all relevant molecule at the relevant sites and solve their solve the entire structure in one go. Then that will give a tremendous help to us to determine the three-dimensional structure of the entire living apparatus that is working inside our cell. So we are at present at this stage. We want to conquer this total structure of all these macromolecules or biomolecules present inside the cytoplasm of cell. So this is all about protein crystallography. And there are few slides are there here. I want to go to lipid crystallography as soon as possible. So you can read it on by your own. So how diffraction pattern was generated, what is the procedure. So first the main bottleneck of X-ray crystallography is always getting a sufficiently large, that is around 1 mm diameter, good quality crystals. So after the crystal structure is obtained, it will put in the X-ray. We generally usually a single monochromatic X-ray, either in-house or in the cyclotrons, and we used to get all the spots, and after we get all the spot, we solve all the spot to get the structures. And applications are varied applications, and there are some limitations are also there. Small molecule crystallography typically involves crystal with fewer than 100 molecules in their asymmetric unit. Each crystal structure are usually so well resolved that the atoms can be discerned and isolated like blobs, but in macromolecular crystallography often involves tens and thousands of molecules inside the unit cell. Such crystal structures are generally less well resolved. Even if it is still less well resolved, we can get a resolution which is close to 1.5 to 2 angstrom, and which is quite good in solving the three-dimensional structure of the protein. So it is less, but it is not worst. Still, it is very useful in the solution of the protein structures. Okay. So this part is over. Now we are coming to the lipid crystallography. So as we told in the previous section, in case of protein, we can make the solution, dry it up in the chamber, and as the protein precipitates, it may form crystalline structure. So in this is a proper crystalline structure with lattice. Suppose this is any protein, I don't know what protein I am drawing, but it can form regular repeating structure having millions of layers of the protein molecules. But in case of lipid, the trouble is that the lipid structure that we are going to study is the lipid bilayer structure, and the lipid bilayer does not form crystals unless it is useless, because it has to stay fluid. Correct or not? Hello?
Yes, sir.
Okay. So now what we want from this crystallography technique about this lipid bilayer. So we want few parameters, and if the lipid this technique of X-ray crystallography can give us that, then it will be well and good. So what kind of information we want? We want the distance between these phospholipid molecules, phospholipid or any other lipid. You can take sphingolipid also, no problem. The regular, it is in membrane, they are in regular repeating arrangement, but the trouble, the membrane is only 2 layer thick. It is, as we discussed, it is the second sort of structure, though there are some arrangement is there, but this arrangement is totally local. There is one membrane, another membrane, in between there is no arrangement. So crystallography is difficult but not impossible. So, and what information is required to draw the three-dimensional structure of this membrane, that we have to first look into. If that can be done easily by crystallography, we can use crystallography to solve the structure of the biological membrane. So, to draw this, we need to know first of all the distance between these phospholipid head groups. This distance we want. What next we want? We know whatever lipid is present over there. We can do a simple biochemical assay, and we can conclude whether it is phosphatidylcholine, phosphatidylethanolamine, etc., etc. We need how much these lipids side chains are twisted. This is one form of the membrane lipid. This is another form. Rotated by an angle. So, to draw the three-dimensional structure of the membrane, we need to know this angle by which it is rotated from the perpendicular axis of the membrane. If these two information is there with us, we can draw the membrane. Correct or not?
Correct, sir.
Okay. So, X-ray crystallography can help us. How? So, this has been taken from papers. So, there they were using nickel filter copper. What is Ka? Ka, what metal it is? Beryllium most likely. Gallium. Okay. So, it is copper gallium X-ray radiation, and these are the parameters. So, these parameters are used to get the X-ray, and membrane was made up with DPPC. So, full form of DPPC, what is that? I should have been written over there. DPPC is dipalmitoyl phosphatidylcholine. So, it is a phosphatidylcholine. So, it's a phospholipid, and there are two palmitic acid attached as the side chain, the hydrophobic chain. Okay. So, this is phosphatidylcholine. This phospholipidylcholine is made into a bilayer, and I will give you a paper in that they studied the various stages of this phosphatidylcholine, that is those amorphous stage, semi-crystalline stage, gel stage. So, they made a very thorough study of at what temperature it goes semi-crystalline, what temperature it remains as fluid, what temperature it remains as gel. So, this is very well characterized for this DPPC. So, this DPPC is used to make a bilayer. So, one bilayer is formed. So, now we want to know what is the spacing between these phospholipid head groups in the bilayer, and whether the bilayer is inclined to the perpendicular axis of the biological membrane. These two questions we are asking. So, a thin bilayer was put on a dish and X-ray beam was shined on it. Okay. So, To reconstruct the structure of a molecule, in this case lipid bilayer, one must accurately determine the various structural factors, a very big expression. Since the structural factor Fh is a complex number of magnitude Fh and the phase term is a very complex term, it is not possible to examine experimentally measure Fh directly. This presents us with the infamous phase problem. However, a surprisingly large amount of information can be obtained by simply determining the position and analyzing the shape of the X-ray maximum of the X-ray diffraction pattern of this particular bilayer. So, direct solution was little bit problematic, because for that you need to calculate the structural factors, but without going into that, just after shining the X-ray and getting the X-ray diffraction pattern, we could get very useful information about the structure of the lipid bilayer. How? So, this is the arrangement, this is the diffraction pattern what we get from the structure for the lipid bilayer. You see there are two spots, correct? One big spot here and one big spot there, and there are spots at regular interval in this C axis, correct or not?
Yes, sir.
So, when we put X-ray, we put X-ray along various plane, like in crystallography terms they call 1 plane, 1 0 plane, 0 1 plane. So, those are little bit more complex concept. Anyway, I will give you the one video, if you are willing, you can see that. But one thing is very interesting what is happening over here. So, this is the 3D diffraction pattern obtained by L beta 1. It is a particular phase of this DPPC bilayer collected using an image plate recorder. The 1 reflection, this one is making a 27-degree angle with the equatorial axis. So, this is the equatorial axis, the axis that is perpendicular to the C star axis, and it translates to hydrocarbon tilt angle theta, which is around 32 degrees. So, from this tilt axis there is a formula that can be translated into how, at what angle these hydrocarbons chains are tilted with respect to the perpendicular axis of the membrane. So, here just by looking at the figure, they told that this angle is 32 degrees. So, there is a mathematical expression that connects this 27-degree angle with the tilt angle. Let me see whether I can show you that. It was there with me. Is it this one? No, not this one. Another paper. Let me just find out the mathematical expression for you. Just a second. It will be. It is important. No, this is not that one. Yes. No. Oh, this is the particular angle things that I was telling you. So, it can be straight or it can be tilted. This angle can be directly find out by that psi angle between the 1 plane and the perpendicular plane. But I want that expression. It was there in my folder. Yes, this one. I'm It is figure 2. Just a second. Yes, this is the equation. It's a Bragg's law. H lambda 2 sine beta, not this one. It is there in this paper. It is just a simple trigonometric expression. Anyway, I'm not getting it. If you're interested, see in this paper. It is there. How it get translated with the tilt angle, and tilt angle is very important because it can tell you what state the lipid is there. This is point number 1. And point number 2, again, along the C star axis lie the Bragg refraction as a result of the lamellar repeat of distance d. Can you see that there are small spots, correct, at a regular interval?
Yes, sir.
So these are the distance between the two phospholipids present in the membrane. So this is the lamellar repeat distance. So we are getting how far they are and at what angle they are tilted. So by simply taking an 2D X-ray diffraction pattern of an oriented lipid system and doing some very simple measurement, we can able to determine the following: the hydrocarbon chain tilt angle, the direction of the tilt with respect to the quasi-hexagonal hydrocarbon chain lattice, and the bilayer repeat spacing d, and the fact that these systems are not 3D crystals, but rather than they are 2D structures. So since they are 2D structure, by without going into Fourier transformation, but just looking at the X-ray diffraction pattern, we can extract out very useful information. And not only that, it is 2D, and also it is a symmetric structure. You see that if you draw a line from here, the top and bottom are mirror images to each other, correct or not?
Yes, sir.
So as it is symmetric, then this big equation that we are telling about the structure factor, it also gets simplified. So as mentioned in the earlier section, the structure factor has a magnitude of Fh, and there is a phase equation. Although Fh is a measurable quantity, the phase equation is not and can assume any value between 0 to 2 pi. The only one phase angle being correct for the given Fh. However, if the structure is centrosymmetric, as we can get in case of membrane, this then the Fourier transform of centrosymmetric function is real, and this measures the structure factor Fh is given by either plus Fh or minus Fh. So this term no longer is applicable for membrane. So our solution of the structure becomes free from trouble doing a Fourier transformation. And as can be appreciated, this simplification of structural factor greatly reduces the complexity of the phase problem. Finally, Fh become plus minus IH, where IH is the intensity of the Bragg's refraction. So from Bragg refraction directly, you can measure the relative electron density along the length of the plasma membrane. So this is the relative electron density of the membrane. You see there are two peaks over there. So these two peaks are the two lipid bilayer, and this is the these two peaks are the d spacing as we have discussed, and this is the bilayer normal, and this angle gives you the tilt angle. So this is the distance between the two phospholipid head groups, and this is how it is tilted. And you can see that one minima is coming. So this minima gives you the bilayer normal. So if it is if this phospholipid is if it was staying straight, then this length could have been 90 degree, the theta. Now the theta is less than 90 degree. So it indicates that this is the phospholipid head group. So this phospholipids is arranged like this, and this is the d spacing between the two phospholipid bilayers. Did you get any hint? Did you get the point? So if the layer is like this, just put your hand. So this is the d spacing, the distance between the two phospholipid head groups, and this is the actual electron density map. We can get that without doing a Fourier transformation because the structure is centrosymmetric, but in reality it is tilted. And how can we make that? So when you put the structure of the phospholipid, you have to tilt it. It is not getting filled in this map directly. You have to tilt it to make it fit, and this is the tilt angle. So this, and how come you get this structure? You will get this structure because you know the biochemical composition of the membrane. So to fit the membrane, you have to tilt it. And how can you get the tilt angle? Just compare it, measure it with the tilt from the bilayer normal. Did you get any hint? It is bit complex. I also understood
Yes,
this
sir.
much only. So the take home message is, by applying X-ray crystallography, we can also solve the arrangement of lipids at various phases of the lipid bilayer. It is important because in case of differential titration calorimetry, DSC, we can find out how many phases are there, but we don't know what is the status of the phospholipids on those stages, whether they are straight or they are tilted. But if they start moving like a fluid, then this technique will not work. But if it is crystalline or semi crystalline or gel phase, that they are actually located at a particular location, then by applying X-ray we can find out the spacing between the phospholipid head groups and the angle by which these lipid groups are tilted. Okay, so with this we finish both crystallography and the lipid module. Next class we are going to finish one more technique of the last module. Okay, then any questions?
No, sir.
Okay, so it's a marathon class, and see you tomorrow.
Sir, did you receive all the practicals?
I'll check it up.
Okay, sir. Thank you.
Thank you, sir.